Hello everyone, welcome to my channel. So in the last session we have seen about the electric dipole, its field in an equatorial line as well as along the axial line. Today we will see dipole in an external electric field. In an external electric field. It is a simple equation. So what you have to do is consider a dipole which is placed in an external electric field. Dipole means you have minus q and plus q, equal and opposite charges separated by a distance of 2a. So this much distance is a and this is a. Okay. Say that there is a force minus QE acting and electric field is in this direction. Minus QE is acting downwards and here the force acting on this charge is plus QE. So in total, the total force is 0 or the net force acting on the dipole is 0 because it is minus QE and plus QE, equal and opposite forces. So in total they will cancel. But if you consider that in an electric field which is separated by some distance, say total 2a, so there is a force acting on the whole system and it makes the system to rotate, which is called as torque. Okay, that means couple is acting, equal and opposite forces act at two different points and they make it to rotate like this. Okay. So this is what. Now if you consider at this point, say that it is rotating in this way, the force or the couple acting on the system will make it turn in this manner and we need to consider this angle theta, and in order to consider the torque which is represented by the symbol tau, torque tau, okay, you have to consider the perpendicular distance between two anti-parallel forces. So this one and this one. We get it as 2a sine theta. You have theta here, a and a, you complete it together, you get 2a sine theta. So the total force is 2aq into sine theta. What is this q? Any one of the charges. So 2aq sine theta into which one you have? E. Correct? Electric field E. I'll not mention it in the vector form. Okay? 2aq sine theta into the electric field, external electric field. What is this 2aq now? I can write it as dipole moment which is represented as P. Okay? So P sine theta into E. Okay. If I want to represent in vector notation, so it is tau is equal to P cross E. What is this? Cross product. So P cross E. P E sine theta, where P is the dipole moment acting on the system. So minus P, minus Q to Q, you have this moment acting, which I have discussed initially when I used to discuss about the dipole. Okay, so minus q to q we will just represent it as P. Okay, so now torque tau is equal to P cross E. So it is PE sine theta. So this is regarding dipole in an external electric field. Okay, I hope it is clear. We will move further with the next topic. Continuous charge distribution. So this topic is important for 2 marks. Dipole in an external electric field. So next is continuous charge distribution. We have 3 different definitions here. First is linear charge distribution, surface charge distribution, and volume charge distribution. So linear, as the name implies, line element you need to consider, surface, any surface area, volume as a whole volume, okay, three-dimensional kind. So now linear, I will consider a simple wire, in that a small portion. Let us represent it as delta L. Delta represents very small, the small portion. Now for the surface, we can consider this any square shape or rectangular shape. In that you can consider any small area, represent it as delta A or delta S. We will write it as delta S. Okay. Volume, any three-dimensional kind. In that you consider this volume as delta V. Here we have to calculate the charge distribution. How is the charge distribution? So in discrete components it is very simple. So as a continuous form, so if you consider very small elements like this, n number of elements, as a together we have to consider in a continuous form. The same way here also volumetric. So how we will represent? Linear charge distribution is represented as lambda, surface charge distribution as sigma, and volume charge distribution as rho. Lambda, sigma and rho. So these two we will be using in the application of Gauss law. So please keep in mind. So lambda, sigma and rho. So whenever we consider this linear charge distribution, how is the charge distributed with respect to the electric field? So if you have any electric field along any direction, if you want to consider this direction, so how is the charge distribution taking place here in case of linear charge distribution? So instead of discrete or separate, we consider it as a whole or in the continuous notation. So now lambda, delta Q divided by delta L. What is delta Q? Delta Q is the small charges, whatever may be the number of charges. So it is, since we are considering very small element, here we consider charges also very small. So it is a ratio of charge to the length or the line element which we consider here. So what will be the SI unit of linear charge distribution? It is coulomb per meter. Coulomb per meter. Similarly, you have surface charge distribution which is represented as sigma. So sigma will be delta Q divided by delta S. Delta S is the area element. So if electric field is in this direction, so the number of charges are delta Q here. So it is sigma is equal to delta Q divided by delta S. What will be the SI unit? Is coulomb per meter square. Delta S is the area, surface area. So it is coulomb per meter square. Similarly, volume charge distribution, rho is equal to delta Q by delta V. So its SI unit will be coulomb per meter cube. So these are the three different definitions and three different explanations for linear, surface and volume charge density. It is lambda, sigma and rho, where we represent delta L for linear, delta S for surface area, delta V for whole volume, what you have to consider. So lambda is equal to delta Q by delta L coulomb per meter. Sigma is equal to delta Q by delta S coulomb per meter square. Rho is equal to delta Q by delta V coulomb per meter cube. So this is regarding continuous charge distribution. Moving further, we will go with the Gauss law. Okay, Gauss law deals with the electric flux and charges. It's a small derivation. So move on further with the next topic, that is Gauss law. This is important. Gauss law is important. Okay. You consider any volume. I will consider the sphere. In that we will represent one small surface area. This one. Let it be delta S, and this is the direction of the electric field. Okay. Oh, if I consider. Now, how is the charge distributed or the electric flux through this surface area? Since it is sphere, let us consider it as radius r. Okay. So this position vector will be r, vector r. So it is same throughout because we are considering the sphere. Now, what will be the electric flux definition? So flux phi is equal to E dot delta S. E dot, what is area here for the sphere? It is 4 pi r square. I will consider delta phi because delta phi means only for this area which we have considered, small area. If I want to consider for the whole sphere, I have to consider the whole surface area. Okay, so instead of directly writing this one, after summation, then we can write this one. Okay, I'm sorry. So this is delta S. If I want to consider the total flux throughout the sphere, what I have to do? So it is summation of E dot delta S. So what is E? It is 1 by 4 pi epsilon naught Q by r square into summation of delta S. We have to consider the summation of delta S because we are not considering this one. Delta S has to be added for the whole surface area, whole area of the sphere. So now it is flux phi is equal to Q by 4 pi epsilon naught into r square into summation of delta S. Surface area of the sphere is 4 pi r square. So 4 pi r square will be cancelled. So phi is equal to Q by epsilon naught. This is the Gauss law. So it tells about the distribution of charges in the sphere or any area, any shape which you consider. So phi is equal to Q by epsilon naught. So Q is the total charge on the whole system. So it is Q by epsilon naught. This is regarding Gauss law. Important concept and important definition also. So please keep in mind, you have to consider the surface area, smaller surface area, then add it for the whole surface. So you get Gauss law. So delta phi for the smaller area which you consider, and for the whole sphere if you want to consider, you have to just add. Same way how we will use in the application. So application of Gauss law, we have 3 applications, simple applications. The concept used is phi concept, that is electric flux, and then continuous charge distribution. If you consider a linear or a straight wire, we will be using linear charge distribution. If you consider any rectangular shape or any cardboard kind of thing, then we will be using surface charge density. So in our syllabus we have linear and surface charge density concept as an application of Gauss law. Okay, so we will move further with the last concept of this chapter. So that is application of Gauss law. So we will move on to the application of Gauss law. 3 applications. These are very important. So first one is field due to an infinitely long straight wire. long straight charged wire. This is important. Small derivation. How we will calculate the field, total electric field due to an infinitely long straight charged wire using Gauss law. So first consider an infinitely long straight wire. So it is very thin, so just for our purpose we will consider little thick. So we will consider positively charged. So if it is positively charged, the electric field is radially outwards. So this is just the surface which we consider. Say that electric field is like this. So here it is outward, here also outward. So that means this and this will be cancelled. Only thing what we have is here, along this side. Okay. So it is charged outwards. Point P, if you consider on the surface of the cylinder, it is in the form of the cylinder. So it is charged faced outwards if the charges are positive in nature. If it is negative, it is towards it. Okay. Which one? Charge density. Charge density. How we will represent charge density? By the symbol lambda. Okay. Lambda is equal to Q divided by L. This is what we have to keep in mind. Lambda is equal to Q by L. Okay. So now electric flux using Gauss law definition. Phi is equal to Q by epsilon naught. Phi is equal to Q by epsilon naught. This is using Gauss law. But what we have the flux phi definition? E dot delta S. E dot delta S. So phi is equal to E into 2 pi RL. What is this L? L, we will consider this length. R is this R. Okay. So it is 2 pi R, 2 pi R and the length L. 2 pi RL. So now substitute this one. That is 2 pi RL into E. E is electric field which is facing outwards is equal to Q by epsilon naught. But according to the linear charge density, what is Q? 2 pi RL into E. Q is equal to, we have the definition as lambda is equal to Q by L. So Q will be equal to lambda L divided by epsilon naught. So L will be cancelled. E is equal to lambda divided by 2 pi R into epsilon naught. So this is the expression for electric field for infinitely long straight charged wire in terms of linear charge density. So it is E is equal to lambda by 2 pi epsilon naught into R. Okay, you can just rearrange. If you want to write in terms of vector, so it is vector E is equal to 2 pi vector R into R cap, or N cap also you can write. So if you don't want to represent in vector, just in terms of scalar quantity, it is E is equal to lambda by 2 pi epsilon naught into R. So this is the expression for total electric field for an infinitely long straight wire using Gauss law. This is very important. Represent the diagram very clearly and then write all the steps. So whenever you are using this one, say that using Gauss law. Then whenever you use this concept here, say using the concept of linear charge density. So next, second application is field due to an infinitely long charged plate. So first one and third application is very important for the examination point of view. Second one is not that important, but still you have to know the concept where we use the concept of surface charge density. Okay, field, second one. Field due to a uniformly charged charged plane sheet. So here we will be considering the concept of surface charge density. Just a box kind you just consider. In that we will be considering the surface charge. Consider just one simple sheet, okay, where we have delta S. So whenever we represent the surface charge density, how are we going to represent? Sigma. Sigma is equal to Q by delta Q by delta S. Okay. So now this, if we consider in the middle, this we will take it as plus X direction, where E is this electric field and E is here along minus X direction. Okay, just for our reference. So if we consider this as origin, plus and minus, but it is minus of minus, so the total electric field will be 2E. Okay, this is already minus, so this is in the opposite direction. So minus of minus, when you add together, the total electric field what we consider is 2E. And what will be the surface area? If we consider the surface area, this area as A, so it is 2EA, or the total electric field. Now using the concept of Gauss law, phi is equal to Q by epsilon naught. Phi is equal to Q by epsilon naught. So what is this phi? So phi will be 2EA is equal to Q by epsilon naught. What is Q according to surface charge density? So 2EA will be equal to, we have surface charge density sigma is equal to Q by A if we consider. So Q will be equal to what? Sigma into A. A will be cancelled. So E will be equal to sigma by 2 epsilon naught. You have here sigma A by epsilon naught. So E will be equal to sigma by 2 epsilon naught. So this is the expression for electric field for uniformly charged plane using Gauss law. Okay, and also using the concept of surface charge density. Now the last application is for the sphere. Here we have two parts. One is inside the sphere and another one is outside the sphere. This third application is very important. Field due to a uniformly charged thin spherical shell. Field due to uniformly charged thin spherical shell. Let us consider a very thin spherical shell. So it is very thin. Okay. And first, let this radius be R, capital R. We will consider a point outside the spherical shell whose radius vector is small r. Two parts. So this is the first one where r is greater than radius. So when we consider this first part where r is greater than small r, capital R, so that means field outside the spherical shell. Okay. So summing over the whole surface area. Okay. What we get? E dot delta S is equal to Q by epsilon naught. So E into 4 pi r square is equal to sigma A by epsilon naught. R square due to this whole sphere. So E into 4 pi r square is equal to sigma by epsilon naught. What is A? A is this inside one, capital R square. So 4 pi and 4 pi will be cancelled. So electric field outside the spherical shell at any point is sigma by epsilon naught into capital R square divided by small r square. Okay. This is the expression for the field due to an uniformly charged spherical shell outside. So this is the first part. Now you have to consider inside. Same like how we considered outside, let us consider an imaginary sphere inside the spherical shell whose radius is r only. Clear? So the second part is main point. What has to be considered here is what is the charge enclosed inside the sphere. How much is the charge enclosed inside the spherical shell? So this is capital R. Let me consider one more imaginary sphere inside whose distance is small r at point P. Okay. Now what about the electric field at this point inside the spherical shell? So same like how we consider. So flux phi is equal to Q by epsilon naught. E into 4 pi r square is equal to Q by epsilon naught. So what is this Q enclosed by a spherical shell? So no charges are inside the sphere. So charge is 0. That is why E is equal to 0 at any point inside the spherical shell, thin spherical shell. Charge enclosed is 0. So wherever point you consider inside this one, the electric field is found to be 0. So this is the second part in this third application. So this is point B where small r is less than capital R. So this is very important. So first one is due to the thin long straight wire, charged wire. Second one is for the thin sheet. Third one is for the spherical shell. So for the last two applications we are using surface charge density, and for the first one we are using linear charge density. Here those two are sigma and the first case is lambda for the linear charge density. So this is regarding application of Gauss law. Okay. If you want, you can write all these in vector form also, vector notation also. So where you have to consider unit vector r cap. So in the previous case also we have to consider r cap. Okay. So even in the LHS you have to represent it in the vector form if you are representing in the vector form. So this is regarding the concept of electric charges and fields. In the next session we will discuss regarding the numericals, exercise questions based on this chapter. Okay. Thank you.